Welcome to 11th lectures on terpenes and terpenoids. In this lecture series, we are going to discuss the chemistry of three diterpenoid molecule. First one is a phytol, second one is a abietic acid, and third one is vitamin A. In previous lecture, we have discussed the chemistry of the phytol molecule. Now in this lecture, we are going to discuss about the chemistry of abietic acid. We will see the occurrence as well as uses of abietic acid. We will discuss the structure of abietic acid on the basis of chemical methods of analysis. The structure of abietic acid is relatively complex, and therefore we will have to perform more experiments, more chemical experiments for structure determinations of the abietic acid. Now, in this structure determination, we will come across some important concepts in organic chemistry like oxidations with sulfur or selenium. So, dehydrogenation or the oxidations of terpenoid molecules with sulfur and selenium gives aromatic compounds. The structure of these aromatic compounds can be elucidated on the basis of oxidation experiment, as well as it can be the structure of this aromatic compound can be supported by its synthesis by the methodology called as Haworth synthesis. So we will discuss the Haworth synthesis of two aromatic compounds. One is retene and homoretene, which are formed during the dehydrogenation. Abietic acid is a diterpenoid containing the two double bonds. So we will study the UV visible spectroscopy of abietic acid molecule, and in that case we will apply the Woodward-Fisher rule for the calculations of the lambda max. Now let us see from where we get the abietic acid. The major source of the abietic acid is resin acid, which is present in pine wood. Resin acid refers to a mixture of several related carboxylic acid with abietic acid as a primary component. All these resin acids is having same basis skeleton, that is that three fused rings are there, and they are having the same empirical formula C9H29COH. These structures can isomerize into one another. Resin acids are tacky yellowish gums that are water insoluble. They are used to produce soaps for diverse applications. Now let us discuss the structures of terpenoids on the structure of abietic acid on the basis of chemical methods of analysis. Elemental analysis has shown that the molecular formula of the abietic acid is C20H30O2. Now from this molecular formula we get lot of information about the structure of abietic acid. Since it contains 20 number of carbon atom, it means that there are 4 isoprene units. And according to the special isoprene rule, these 4 isoprene units may be joined through head to tail linkage. Now, since it contains 4 isoprene unit, it belongs to a class of diterpenoid molecule. So, just by counting the 20 number of carbon atoms, we get a broad idea about the structures of this abietic acid molecule. Another information that we get about the structure of abietic acid from molecular formula is the degree of unsaturations or double bond equivalence. Double bond equivalence or the degree of unsaturation is related to how many double bonds or the how many rings the molecule contains. It is calculated by the formula x plus 1 minus y by 2. So if you keep the values of carbon and hydrogen, then the degree of unsaturation is found to be 6. So degree of unsaturation in abietic acid is 6. It means that it may contain the 6 double bond, or it may contain the 6 rings, or it may be the combinations of double bond as well as ring. So in the incoming investigations, we have to find out this nature of unsaturation. Now let us directly switch over to the analysis of oxygen. What is the nature of this oxygen in abietic acid? Now since it contains two number of oxygen, one can suspect it to be a carboxylic acid or an ester. Therefore, some reactions of carboxylic acids are performed. For example, abietic acid is treated with sodium bicarbonate. In this experiment, effervescence of carbon dioxide was observed, and because of this effervescence, we assume that the abietic acid is an acid, is a carboxylic acid. Then since it is a carboxylic acid, one must expect an esterification, and when esterification was attempted, it was found that esterification was found to be the difficult. Now since esterification is difficult, we may assume that the carboxyl group may be sterically hindered, and in other words we can assume that the carboxylic acid group in abietic acid may be of tertiary carboxylic in nature, tertiary nature. Then the third evidence that we get from this about the carboxylic group is the treatment with warm H2SO4. So when abietic acid is treated with warm H2SO4, it evolves carbon monoxide. So again it proves now that it contains a tertiary carboxyl group. So on the basis of these three experiments, we have now proved that Abietic acid is a carboxylic acid, and more specifically it's a tertiary carboxylic acid. This tertiary carboxylic acid corresponds to 1 degree of unsaturation. So out of 6 degree of unsaturations, we have accounted for 1 degree of unsaturation. Now we can rewrite the molecular formula of the abietic acid since it contains COH as C19H29COH. Now let us switch over to the analysis of unsaturation here. We have to prove that how many double bonds it contains. So for that, abietic acid is subjected to hydrogenation. On hydrogenation, abietic acid forms tetrahydroabietic acid and its molecular formula can be written C20H34O2. If we subtract the molecular formula of the abietic acid from tetrahydroabietic acid, we find that abietic acid has consumed 2 molecules of hydrogen. Now, since it has consumed 2 molecules of hydrogen, abietic acid contains 2 double bonds. So, in this way, we have accounted for 2 degree of unsaturations in abietic acid. Now, let us make some chemical arithmetic. The parent hydrocarbon of hydrogenated abietic acid, that is C20H34O2, or in other words C19H33COH, because we can rewrite the molecular formula in this way. Its parent hydrocarbon is C19H34 and C19H34 corresponds to the general formula CnH2n-4. Now CnH2n-4 corresponds to the tricyclic saturated hydrocarbon. So here is a revision of the fundamental. CnH2n plus 2 corresponds to acyclic saturated hydrocarbon. CnH2n is a monocyclic, CnH2n-2 is a bicyclic, and CnH2n-4 is a tricyclic. So just on the basis of hydrogenation experiment and the chemical arithmetic, we have proved that abietic acid is tricyclic in nature. Now tricyclic in nature corresponds to 3 degree of unsaturations, and therefore in this way we have accounted for 6 degree of unsaturations in the abietic acid molecule. 1 degree of unsaturation is for CO2H, 2 degree of unsaturation is for 2 double bonds, and 3 degree of unsaturation is for the tricyclic nature of the abietic acid. Now with this information in our hand, we can now, this is a major information we have got. Now we have to find out the skeleton of the abietic acid, and in this skeleton we have to assign the positions of 2 double bond as well as CO2H, and in that way we can reach to the structures of abietic acid. So to prove the skeleton of the abietic acid, a dehydrogenation experiment is performed. Dehydrogenation of abietic acid with sulfur or selenium gives a compound called as retene. It is having molecular formula C18H18. This structure of the retene was proved on the basis of this oxidative degradation sequence. And another proof for the structure of 1-methyl 7-isopropyl comes from its synthesis using Haworth methodology. In the oxidative degradations, that is in this degradation experiment for the structure determinations of this retene, we came across this 1,2-diketone, benzo 1,2-diketone, and this 1,2-diketone undergo benzylic acid rearrangement in presence of KOH followed by decarboxylation. So we get a fluorinone derivative, and fluorinone on reactions with the KOH uses a tricarboxylic acid. So in this way, we have reached to the structures of 1-methyl isopropyl phenanthrene on the basis of this oxidative degradation experiment. And another proof that we get about its structure of retene is from the synthesis. So synthesis of retene can be accomplished from naphthalene. Naphthalene is subjected to Friedel-Crafts alkylations, and because of the isopropyl group, the beta position alkylation occurs. Then succinic anhydride AlCl3, it undergoes Friedel-Crafts acylation reactions. We get a keto acids here. This keto acid is esterified, and then this is treated with only one equivalent of the methyl magnesium bromide. It will introduce the methyl group that we require at the end. Later on, its hydrolysis is CO2H group will be free here. Double bond is reduced, and then another Friedel-Crafts reaction occurs. We get a tetralone derivative. Tetralone derivative is subjected to Clemenson's reduction, and we get a retene molecule. So the structure of retene molecule is proved on the basis of oxidative degradation experiment as well as its synthesis by using Haworth methodology. Now this structure of retene is a very useful information in understanding the skeleton of abietic acid. From the structure of retene, we can assume that Abietic acid is having a phenanthrene skeleton with the positions of methyl at 4 positions and isopropyl group at the 13 positions. Now, retene molecule corresponds to total 18 number of carbon atoms. Here is the 18 number of carbon atoms, and the 2 carbon atoms are lost during the dehydrogenation experiment here. Now, these 2 carbon atoms which are lost are likely to be a carboxyl group as well as the angular methyl group, because it is well known fact that the decarboxylation occurs during sulfur or selenium dehydrogenations, as well as the angular methyl group is lost in the form of CS3SH. So chances is that whatever the 2 carbon atoms are lost, they may be a angular methyl group and the carboxyl group. So in this way, we have come a very long way as far as the structures of the abietic acid is concerned. We have proved that it contains a phenanthrene skeleton with methyl and isopropyl accounting for 18 number of carbon atoms. And in this skeleton, we have to now assign the positions of one angular methyl group, then 2 double bonds as well as the carboxyl group. Now let us find out the positions of one missing carbon atom, and we assume it to be the angular methyl group because it was lost during the dehydrogenation. Now in this case, oxidations of abietic acid is performed and we get tricarboxylic acid. These are the two isomeric tricarboxylic acid. Sorry, these are not isomeric. We get two different carboxylic acids. Now this tricarboxylic acid, and out of 3 carboxyl group, one carboxyl group is already coming from the abietic acid. So these two carboxyl groups are likely to form due to the oxidations of the carbon-carbon double bond, which may be present in ring B and C of the phenanthrene molecule. The structures of A and B was proved, and subsequent dehydrogenation with selenium has given 1,2,3-trimethyl benzene as well as metazylene. The relationship between 1 and 3 clearly indicates the presence of angular methyl group at 10 positions. Then and only then we will get here metazylene kind of the product here. It's a metazylene, and again it's a 1,3-dimethyl, 1,2,3-trimethyl benzene is formed. So oxidative degradations of abietic acid with KMnO4 forming two isomeric carboxylic acid has informed lot of things. First of all, the presence of methyl group at 10 position because we got such aromatic compound. Secondly, the ring A is intact during the oxidations. It means that these two rings are cleaved, and the cleavage of these two rings is possible only when we assume the presence of double bonds in ring B as well as ring C. So in this way, we have concluded that double bonds may be present in ring B as well as C, and we have proved the positions of angular methyl group at position number 10. Now let us find out the positions of the carboxyl group. And for the positions of carboxyl group, very simple experiments were performed. Abietic acid is esterified, CS3, CO CS3 group we get, then reductions gives us CS2H, and it undergo rearrangement reaction in presence of PCl5. Oxygen it is completely removed from this, we get C19H32, and then it undergo dehydrogenation, we get a homoretene. Here retene contains 18 number of carbon atom and homoretene contains 19 number of carbon atom. One extra carbon atom is accommodated here. Perhaps this carbon atom may be coming from the carboxylic acid here. And the structures of the homoretene was again found on the basis of oxidative degradation as well as its synthesis by using Haworth methodology. It is observed that retene and the homoretene, both of them give the same oxidation product, and they contain one carbon atom. Retene contains one carbon atom less than that of the homoretene. Therefore, one may assume that here is our one carbon atom, additional carbon atom, that's a ethyl group here, and that is the structures of the homoretene. Further support for the structures of homoretene comes from the Haworth synthesis, which is very much similar to the synthesis of retene, except that instead of methyl magnesium iodide, here ethyl magnesium iodide was employed. Now, if you assume the COH group at this position, then one can understand the formations of homoretene very easily. Reductions will give us CS2H, and in presence of PCl5, it undergo Wagner-Mirwin rearrangement. We get ethyl here, and this on dehydrogenations will give us homoretene. So in this way, in the phenanthrene skeleton, we have proved now the positions of CO2H group. which is a tertiary carboxyl group. Now, after getting the positions of the COH group, in this way we have progressed. Now we have we got the positions of the angular methyl group as well as we got the positions of the carboxyl group. Now it's time to find out the positions of two double bonds, and for that we are having two evidences. One is the Diels-Alder reactions and second one is a ultraviolet visible spectroscopy. Now this Diels-Alder reaction was misleading to the structures of the abietic acid. Abietic acid abietic acid forms an adduct with the malic anhydride when it is heated at 100 degrees centigrade, and this adduct is the same as that of levoamperic acid we get. Now from both the structure it is very clear that abietic acid is also a conjugated, there are two double bonds are conjugated, that's why Diels-Alder product is formed. But it is observed that this abietic acid undergo isomerizations to the levoamperic acid, and this actually participates in a reaction. That's why the Diels-Alder product is identical in both the cases. So this experiment is not convincing, and it cannot be accepted evidence for the presence of conjugations in the abietic acid. Second evidence we get about the conjugations in the abietic acid from UV analysis. Lambda max of abietic acid is 238 nanometer, and 238 nanometer is a characteristics of heteroannular dyne, because for homoannular dyne the value is 253 plus, whereas for heteroannular dyne is 214 plus, and therefore the abietic acid is a heteroannular dyne. For levoamperic acid, this value is found to be 272 nanometer. This levoamperic acid and the abietic acid, they are isomer of each other, but the positions of the double bonds are different. In abietic acid is a 238 nanometer, and for levoamperic acid is 272 nanometer. So on the basis of this, it is very sure that abietic acid is a heteroannular dyne. This heteroannular dynes means in ring number B as well as ring number C, we should have the two different double bonds of the abietic acid. Now, this is a very turning point of investigation as far as the structures of the abietic acid is concerned. When abietic acid is subjected to KMnO oxidations, several products are formed, and among them, isobutyric acid is also formed. We have already proved the structures of the retene molecule here, and in that case the positions of the isopropyl group is fixed. So in this retenes, in this phenanthrene skeleton, the double bond must be attached to the isopropyl group. One can put the double bond at 12 and 13 number carbon atom, or one can put the double bond at 13 and 14 number of carbon atom. Then and only then we will get the isobutyric acid. So the positions of one double bond is either 12 13 or 13 14, and the other double bond is conjugated with that, and please note down that the other double bond is a heteroannular die. So on the basis of this there are various possibilities. If you assume 12 13, then another double bond can be here, another double bond can be between 9 and 11, but these two structures are ruled out because both of them are the homoannular dyne. Now here we are getting 13-14 possibility. We can put the double bond here. Again it's a homoannular dyne. Therefore it is necessary that we should accommodate the another double bond at 7 and 8 position. And this is the, in this way if we put this value here, then put this double bond here, then we reach to the structures of the abietic acid. So finally we have elucidated the structures of abietic acid on the basis of all these evidences. This structure is inconsistent with the various structural feature. It contains a tertiary carboxyl group. It contains the angular methyl group at C10 position, isopropyl group at C13 position. There is a retene formations. It's a heteroannular die and the dyne, and the lambda max for this is 238 nanometer. Now let us make a summary of this investigation. How so far we progress to the structures of the abietic acid. First of all, we calculate the double bond equivalence from molecular formula. Then we did the hydrogenation to prove the presence of two double bonds. Presence of tertiary carboxylic acid was proved on the basis of these three experiments. Then phenanthrene skeleton was proved on the basis of retene formations. Then positions of the angular methyl group was proved on the basis of formations of these two tricarboxylic acid, and the positions of CO2H group was proved on the basis of homoretene formations. So this is all about the structure determinations of the abietic acid. Now once the structure of the abietic acid is proved, here we have to make little revision what we have learned during this abietic acid discussion. We came across dehydrogenation experiment where we get the aromatic substrate from terpenoid molecule as well as the oxidation products of the terpenoids. So abietic acid gives a retene, and retene structure has given us a major clue as far as the structures of terpenoids is abietic acid is concerned. Here the formations of 1,2,3 trimethyl benzene as well as methylene, metaxylene gives the proof for the presence of angular methyl group at 10 position. Now second one is about the Woodward-Fisher rules applied to the abietic acid as well as leumpiric acid. So abietic acid is a heteroannular dye, leumpiric is a homoannular dye, and according to Woodward-Fisher rule, these are the calculations shown. Calculated value is 239 nanometer for abietic acid and observed value is 238 nanometer. And for leumpiric acid, 253 nanometers for homoannular dye. This is 50 nanometer is the increments for alkyl substitution. It is 1, 2, 3 and 4 substitution. This is an exocyclic double bond and expected value is 278 nanometer and the observed value is 275 nanometer. Then another one is about the Haworth synthesis. Haworth synthesis of retene and the homoretene. These two are very much parallel except here methyl magnesium bromide and the ethyl magnesium iodide. So on the basis of this we reach to the structures of retene as well as homoretene. Retene has given us a penanthine skeleton as a clue for abietic acid structure, whereas homoretene has given us a clue for the presence of CO group here. So in this way, we have learned the applications of Haworth synthesis for the synthesis of this very useful aromatic hydrocarbon. So in this way, we have learned the synthesis of structure determination of abietic acid. Now it's time to check our concepts, how much we have progressed in that from the examination point of view. So this is a problem the student should undertake. What are the products of abietic acid with each of the following here? This we have already discussed in the previous slides. Another one is about the synthesis of retene molecule. So this is a sequence mentioned here and the molecular formula of the intermediate products is also shown. So students can also get certain help to reach to the answer of this molecule, answer of this problem. Similarly, the homoretene formation here, the Wagner-Mirvin rearrangement is involved. So students should undertake this reaction sequence also. Now, selenium dehydrogenation, which is very important here, to predict the product of the following reactions during sulfur or selenium. This is also equally important. And last and very interesting problem is about how will you differentiate between the abietic acid and leumpimeric acid on the basis of UV visible spectroscopy. So here applications of Woodward-Fisher rule will be very important, and on the basis of that one can calculate it's a heteroannular diene is a homoannular diene. On the basis of that one can reach to the structure of abietic acid as well as leumpiric acid. So in this way we have learned the chemistry of the abietic acid molecule. Now in the next lecture we are going to discuss about the vitamin A, which is again belonging to a class of diterpenide. Thank you very much for watching the video. Subscribe the video, like the video and stay tuned with the chemistry. Thank you very much.